So far we've been considering sound waves. This is because sound waves travel relatively slowly compared to the speed of light. So the velocity of sound in air varies with temperature, but at room temperature it's around about 343 meters per second. Now light waves, on the other hand, travel at 3.00 times 10 to the 8 meters per second, so a lot faster, which is why you always see lightning before you hear thunder in a thunderstorm, because the lightning travels towards you much faster than the sound of the thunder does. So speed cameras use radio waves, which are part of the electromagnetic spectrum, and so they travel at this faster speed of 3 times 10 to the 8 meters per second. So the same equations apply when we are using electromagnetic waves. You may want to write the equation with a c standing for the speed of light rather than the v standing for the velocity of the wave in the medium, but these have exactly the same meaning. So let's do a calculation now where we'll work out the frequency detected by a radar as a car is travelling past at a very reasonable speed.
So the question is, a speed camera uses radio waves with a wavelength of 3 centimeters. Calculate the frequency of the waves that are reflected off a car travelling at 60 kilometers per hour. Okay, so let's start by drawing a diagram. Here's our speed camera and here's our car travelling away from the speed camera. Now what we're actually going to have to do is we're going to need to break this problem into two parts. So first of all, we're going to imagine that this speed camera is the source of the waves, which it is. It's producing the radio waves and they're travelling towards this car. Now this is the observer. So we can work out that the velocity of the observer is equal to 60 kilometers per hour, which is equal to 60 times 1,000 meters per hour, and divide by 60 times 60, we'll get it into meters per second. So that's 16.67 meters per second. And so we can work out what frequency the observer in the car observes. So that frequency is given by f dash is equal to f. Now in this case, the observer is moving away from the source. So it's v minus v observer over v. The source is stationary, so there's no Vs term here. Now, what we're going to need to know is what's the frequency produced by the source. We're told that the wavelength is 3 centimeters, and so we're going to need to use V equals F lambda, and so F is equal to V over lambda. Now, these are radio waves, so they have a speed of 3.00 times 10 to the 8 meters per second. That's the speed of light, divided by 0.0300. So this is equal to 1.00 times 10 to the 10 hertz. So this is the sound which is detected at the car. But what happens is that sound is now reflected off the car, so the car is now the source, and it is detected back at the speed camera. So the reflected pulse travels back this way. And so the car is reflecting wavelengths with this frequency, f dash, and they go back to the speed camera. So we can work out the frequency detected by the speed camera. It's given by the frequency reflected by the car, so the f dash, which comes from up here. And now in this case, the source is moving, but the observer is stationary. So this is V over V. Now the source is moving away from the observer. So that's V plus Vs. And this is also equal, it's still traveling at 60 kilometers per hour, so it's still 16.67. So let's put these two together now. We've got f double dash, the frequency detected at the speed camera is f dash, which is f times v minus vo over v times v over v plus vs. We simply put this expression here in instead of the f dash here. Now you can see these v's will cancel each other out, and these vo's are both equal to 16.67. So finally, this is equal to 1.00 times 10 to the 10, And now v, that's 3 times 10 to the 8 minus 16.67. This is tiny compared to that. Over 3 times 10 to the 8 plus 16.67. So this is approximately equal to 1.00 times 10 to the 10 hertz. It's a tiny shift, but luckily for us, the speed cameras can detect very, very tiny shifts. So to 3 significant figures, there is no change, but this speed camera can work to many significant figures. So it can actually detect the signal from the car. It can use interference to get exactly what the frequency is.
So now you've seen how a speed camera works. It sends out a radio pulse which is reflected off your car, and it then detects the frequency of the radio pulse which it receives back, and this tells it exactly how fast you are travelling.